courses today, and I kick off with my first lecture. So each of us will give 3 lectures. So my mini course will be on multiscale analysis as an evolving subject, from effective constants to effective dispersions. And I hope you can get sort of clear what I meant by the title as I speak, right? So the second talk will be by Danilo Bekashiko, and so in 1 hour, and it will be on low frequency vibrations of strongly homogeneous elastic structures. No, Ian is speaking. Sorry. Ian is speaking. Oh, apologies. Yeah, you're right. Ian is speaking second. Yuan is speaking second, and his talk is on numerical analysis of high frequency complex equations. Okay, so homogenization and the evolving subject. Okay, so what is homogenization about? We'll hopefully get clear. Maybe not towards the end of today, although some ideas will come up, but perhaps at the beginning of the second hour. So we'll see. So I'll start from a rather basic equation, I hope, that will illustrate where I'm going and sort of will motivate the subsequent discussion. So the equation that I will write now comes from the realm of partial differential equations on the one hand. So it's a so-called wave equation, right? The hyperbolic equation that describes the propagation of waves. We'll start with a homogeneous medium. So there will be no homogenization initially because there will be nothing to homogenize. So we will start with a homogeneous medium, and we will see what sort of features one needs to look at when discussing this wave equation. And I will put this wave equation in the context of a specific application to elastic waves, right? So I chose this because of our connection to tectonics and what's coming in other mini courses and other talks. Of course, you don't need to think about the wave equation in this context. It could be the context of electromagnetic wave propagation, right? And indeed, other setups like sort of a classical acoustic setup is where it describes the wave equation describes the propagation of pressure, right? And there are others, of course. So, but I will look at the context of waves propagating through an elastic medium. So elastic here means that, well, okay, so there is a certain response, a certain resistance to stretching and compression, right? So, for instance, you can think of a piece of rubber, or indeed any kind of solid that we think of as elastic. So, and here I will be thinking about it as occupying the whole space, right? Maybe it's a bit strange, right? It's a huge idealization, but let's just, being mathematicians, let's just think about that for simplicity, so that we can sort of flesh out the main ideas, right? So I'm looking at this sort of equation that is satisfied by a function of 3 variables. So it's an equation in R3. I left these constants here on purpose. Maybe this is not the way some people have seen the wave equation when they open, when they recall what they saw in a book on PDE, so continuum mechanics, right? Maybe you've seen something like this. Right, but of course, that and this is the same thing, provided we divide by rho, and also for a reason, for my own reason, I chose capital U here, right? So I'll say in a second what rho and mu are. And here, delta is the Laplacian that was mentioned yesterday, but yesterday it was Leonardo, in Leonardo's talk, it was a kind of discrete version of this Laplacian that I'm writing here. Okay, discrete and in some sense also one-dimensional. Here I'm talking about continuous in 3 dimensions. Right? So it's just a symbol for this differential operator. So that we don't have to write. We don't have to write this every time. We just use this letter delta. Okay, so we're looking for a function capital U of 3 variables defined in the whole space that satisfies this equation. Oh, and it's a function of t as well. Okay, it's a function of time. So for that reason, time being an additional variable, we sometimes say R3 plus 1, right? So it, the actual language use depends. So people, usually people start talking about it and they kind of work out the common language about referring to this function and to this equation. Okay, so of course there are infinitely many solutions to this, right? So there is still a lot of information missing here in order for me to be able to say here is a solution. Sorry? Yeah, in the whole space, I will need some radiation conditions, maybe, right, and things like that. So for the time being, I'm not gonna talk about them. I'm just interested in what sort of solutions this equation might have, right? So, so in the context of elastic waves, capital U is what people would call displacement. Right? In fact, yeah, okay, so displacement. Displacement, mu is the elastic modulus. And for example, this could be the so-called shear modulus. When this displacement U represents a shearing displacement. Then U is a shearing displacement. So to think about shear, you can just think about a sort of a block of solid rubber, and then you just put something on top of it, and just imagine that it's attached to the surface on which it sits, and then you attach something else on the top, and you just push it like that. So it will take the form of a sort of parallelogram, right? And that's what this word shearing corresponds to. So this piece of rubber has, if it's a kind of nice homogeneous and isotropic medium, it actually has 2 elastic constants describing its response to all possible deformations. One of them is this shear modulus. And in order to measure it, you perform exactly this experiment of shearing that I've described. The other one is the other constant sort of comes in the form of the so-called Young's modulus or the modulus of dilation modulus of a medium, things like that. So there are different ways of accounting for that second constant. Okay, so and rho here in this context is the mass density. Okay, so as I said, in other contexts, these constants may mean something else. Okay, and so I'm gonna erase this now, and I want to keep the equation so we know what it represents. So let's look for some simple waves. Okay, so what do we mean by a wave? So I just want to play with this equation, and I want to come up with some solutions. I don't have any boundary conditions yet, so I have plenty of solutions. And I want to kind of look for solutions that I would like to think of as waves. Okay, so let's look for some simple waves. I put waves in quotes because it's partially my sort of whim as a mathematician to try and sort of model the physical world. I don't know if my description will be adequate, but I hope so. So I'll just look for solutions. Of the exponent of I to the I k dot x. So this is the inner product minus omega t. Okay, so here k is a constant vector, omega is a constant, and I'll try to see whether this equation admits solutions like this under some k and omega that are related to rho and mu somehow. Okay, so and actually, if I plot this, it will look to me like what I would like to call a plane wave. Okay, so this is a so-called plane wave. What it means, so what does the word plane stands for? It means that it looks sort of like an oscillating wave train, if you like. So it's a kind of sinusoid just written in a complex form. So you know it's a sine and cosine. Yeah? And because of this bit, it kind of moves, it propagates. I can plot it, and I can see it moving, and it moves in such a way that at any point on which this is constant, right? So I would like to maybe refer to this as sort of phase of this medium, because it's a certain point on the sinusoid, and this point will be moving. In fact, all points with the same value of this phase will be on a plane, and this plane will just be advancing in some direction. In fact, we will see immediately that this direction is represented by this vector k, and that's why this vector is referred to as the wave vector. So that's where this terminology comes from. That's why I want to call this a plane wave. Sometimes it's referred to as the plane time harmonic wave as well, because it's time harmonic. It's sine and cosine in time as well. Okay, so let me label this by star and double star. So double star is a solution to star. So it's a simple exercise, right? Maybe if we had a bit more time, I could give you a few minutes, just a couple of minutes, just to substitute these answers into the equation and work it out for yourself, right? So, and you would see that this expression is a solution to this equation if minus rho omega squared plus mu modulus of k squared equals 0. If and only if, in fact, right? Okay, so this gives me that omega over the modulus of k is the square root of mu over rho. Where mu and rho are, I introduced them. I mean, they were there from the very beginning, the elastic modulus and the mass density. Okay, and I'm not going into the details of the physical dimensions of these units. You can check them out for yourself. But these units, certainly, I can see what they are, the units of these quantities. So in order for this guy to be just a dimensionless constant number, right? If t is time, and it was time, omega has to have dimensions of inverse time, and k has to have the dimensions of inverse space. There is no other way, right? So I'm forced to conclude that the dimensions, so these square brackets will mean the dimensions of, right? So the dimensions of. The dimension of this quantity is meters per second, right? So it's a kind of wave speed, right? So I expect, even before I ask the physicist, I expect that this should be a wave speed. This represents some sort of speed, right? I kind of also remember, I mean, I probably saw that if I analyzed a bit more in detail this notion of this term plane wave that we discussed 3 minutes ago. Remember, it was the set of points, it was because the set of points with the constant phase was advancing at once. So we would find, if we looked at that more carefully, we would see that the speed of advance would be precisely this speed. And the direction of the advance would be k, the vector k. Okay, so now I'll just note that omega is, okay, so k is the wave vector. The dimensions of the, so modulus of k is the wave number. The dimensions of the modulus of k are meters inverse. So this is basically the number of waves, the number of crests and troughs, right? Crests, the top of the maximum of this wave, and troughs, the minimum of this wave. So the number of crests and troughs, or troughs, right? Per unit length. So it's per unit length, and this is just a number. That's why it's measured in inverse meters. So it's, in other words, it's the spatial frequency, if you like. Okay, so whereas omega is a, sorry? Yeah, this is exactly, yeah. So modulus of k is the number of, so the modulus of k is the number of crests or troughs. So the k is a vector, gives a bit more information. So it's the direction plus the number of crests and troughs. Right? So you have k, and then you have the, this is 1 meter, right? then you have 1, 2, 3, right? So the wave number modulus of k will be 1/3 meters inverse. So and omega is a more familiar object, perhaps something that you sort of come across more frequently in everyday life. It's just what we call frequency, but it's actually time frequency. So it's exactly the same object as modulus of k, but in relation to time. Sorry? Omega is the frequency. Yeah, frequency, the number of crests and troughs per second. Okay, so this is measured in seconds inverse, dimensions of omega per second inverse, and this is frequency. So this is the number of waves, number of crests or troughs per unit of time. So in fact, well, it's kind of interesting that we see there is some kind of duality between space and time already in just these basic objects. And we haven't done that much yet. We just imagined that the wave is described by this kind of guy and try to look at what might come out of it. So in the end, it turns out to take us on the right path to reach a theory, but this is the beginning, right? So yeah, this quantity will be recognizable by people who work with concrete waves as the velocity, the speed of the shear waves. So it's actually one of the two speeds. Remember, I mentioned the second constant. So the second constant, the second elastic constant gives you the second speed, the longitudinal speed or pressure speed, the speed of pressure waves, those due to stretching and compression. And actually, the other one is turns out to be strictly larger than this one. Anyway, so some of us should recognize this from some application contexts. Okay, so the fact, maybe I should actually keep this. So the fact that this guy is constant, so this is just a constant. This is this is a constant speed measured in constant speed. So measured in meters per second. So the fact that it's constant is linked to the notion that we will kind of develop, referred to as dispersion, right? And actually, the fact that it's constant means that there is no dispersion. It's dispersionless, this medium. So because it propagates in free space, homogeneous. So there is these are very simple waves that are not affected anyhow by the medium, right? So no. So of course, well, there is. Well, in terms of losing energy or not, it's kind of also another story, because even if it was non-dispersionless, if it was with dispersion, you would still write the formulation where you should be able to write the formulation where the energy is conserved, right? Because the conservation of energy is a kind of law that we cannot violate, right? So it's a slightly different idea on the side, different question on the side, whether the energy is conserved or not. But the energy is conserved here, yes. So this is a homogeneous dispersionless medium. Actually, the very question of what the energy is already mathematically subtle here. How do you calculate the energy? If you have this exponent, I mean, there is an infinite amount of energy in it. What's the energy? You want to talk about conservation of energy, but what is the energy? I mean, what is the quantity? But we won't go there for now, right? But it's irrelevant. It's a relevant question. Okay, and just to conclude, this part is just to know that as we shall see later, inhomogeneous media, and that will be the next step for us to consider. Right? Inhomogeneous media so something will happen to these coefficients that will so they will not be constant anymore. Right? This will be the next step. That's what the inhomogeneous stands for. Right? So inhomogeneous media always possess some dispersion. And strongly inhomogeneous media even possess something that we would like to think of as strong dispersion. I will make this more clear a bit later, right? More explicit, mathematically explicit. So strongly inhomogeneous leads to strong dispersion. I mean, it sounds like a triviality at the moment, but trivial statement, but it will be fleshed out when they describe what I mean by strong. In what sense? Strongly homogeneous or strong dispersion. Okay, so any questions at this point? So it's a bit of a game at the moment, right? Just nothing. I hope nothing particularly challenging in terms of sort of marks. Right? Just think about solution functions like this that satisfy that equation. So, but I want to make one more observation before I kind of move on to the next part. So, and that is that there is only one natural length scale here. That's important for me. So it's the fact that the medium is homogeneous results in having to conclude, in having to observe that there is no natural length scale except the wavelength. Now, I said that K, the modulus of K, is the number of crests or troughs per unit length. Okay, so can you tell me, I'll give you a few seconds, how I express the wavelength in terms of the modulus of K? I can give you a hint. The length scale is measured in meters because it's a length, the wavelength. Yes.
But then you are going to circle.
I am going
to circle. Because I mean, you look like this concept, which you haven't actually noticed. The unit of length, which is what is the unit of length.
Yes.
So
fine. So yeah, I mean, up to a constant. Okay, I mean, it's still defined up to a constant. So, but I'm gonna. What I wanted to hear is that it's the inverse of the. It's the inverse of the wave number up to a constant factor. And the way I'm going to define it here is that I'm going to write that this is 2 pi over the modulus of K. Right, that's my definition. But what I want to do here is that it's essentially the inverse of the wave number. This is the wave number, remember? So, okay. Okay, so why I make this note here is because I would like to also think about ways of introducing an additional length scale when I want to move to more complicated models, right? So at the moment, it's just waves propagating through a homogeneous medium. I want to kind of think about more complicated setups. They will invariably have to come with an additional length scale. And if I'm a mathematician just looking for models for possible ways of continuing to play with these objects, I have to think about in what different ways this additional wavelength may be introduced, right? And we will see a few different ways of introducing such a wavelength next. So this is the second one. Okay, so maybe I should have put a 1 there at the beginning. So this is the second part. This was 1 here. The second part is ways to introduce another length. Okay, so how? Okay, pretty much half an hour. Great. So, okay, so the first way. Okay, can you think to yourself? Maybe you don't have to say it. Can you think of a way to introduce a wavelength, another length scale apart from the wavelength? Well, I know, yeah. So, but I'm asking the whole the whole audience, right? So, if some of you know several, good. Yeah. Okay, so one way you may have thought about is to consider. Okay, maybe I'll structure this a bit better. I'll write 2 here. One way is to consider a bounded domain, right? So a region, well, it doesn't have to be bounded, but not an infinite free space, right? I can introduce some simple medium with the geometric features, right? Just take a region in space, okay? Bounded region. So I'll just take some region in space, and well, in the actual physical space, it's measured. It has some characteristic length, unless it's very special in some way, like this, right? This is special, right? It will have 2 lengths, 2 characteristic lengths, the thickness and the length. But if it's kind of an object that doesn't have a very unusual geometric shape like this, it will be more or less the same size in all directions, right? And I'll just take one of those. I don't care which one, and I'll label it by L. So the dimensions of L is meters. Okay, I won't talk much about it, you know, from after 5 minutes from now, 5 or 10 minutes from now, because my point ultimately is, well, maybe 15 minutes from now. But my point ultimately is to keep talking about waves traveling through some medium. But here, as you can imagine, we won't have waves in the sense of that we have wave energy coming from somewhere and going elsewhere, right? So here the waves are going to be trapped in this region. And in fact, what we will get is some sort of replacement of the notion of a wave for the case of a bounded region. You may think about the kind of shapes that come up when you talk about resonances, right? Resonant vibrations of a bounded region. So when you take a drum, the circular drum, it has the same length in all directions, in fact. It produces those sounds that we hear, they're resonant, they correspond to some resonant frequencies, and if you looked at this drum in slow motion, you can see some shapes. And these are those kind of waves that I think about for the drum, for the bounded region. Okay, so I'll say that this is a different story, right? This is a different story to what I would like to focus on. Okay, this is what we maybe will call vibrations. Vibrations, that is eigenfunctions. This is a bit specialized, right? So I don't expect everyone to understand this phrase, but you may, if you have heard the term eigenfunction, probably most of you have. Maybe fewer people have heard the word of the term operator, but this term will come later in my mini course. So just let's remember it, right? So in fact, what I will refer to as an operator, it will correspond to a boundary value problem. And this is also certainly maybe perhaps a new term, right? Something still to keep in mind, but something that I can illustrate with a picture, right? So what I will do basically, and okay, so I will think about a copy of this region after non-dimensionalizing. I will explain what non-dimensionalization means here. It means getting rid of all quantities that are measured in physical units. I want ultimately everything to be dimensionless for the mathematical formulation. And I will just take a copy of this region after this non-dimensionalization to emphasize that it's a copy. I'm going to erase this. I'm going to draw it again, and I'm not going to shape it, right? So I would just want to illustrate what a boundary value problem is, right? So you may have seen something like that somewhere. So and I'm going to use lowercase u here rather than capital U, because this lowercase u is what I obtain after non-dimensionalizing. Okay, so it's just a type of problem that we would refer to as a boundary value problem, right? So this is a boundary value problem. Okay, so we have a function u in a region satisfying this equation. We know what delta is. Z is just a constant number. In fact, we can ultimately make Z any complex number. Where does this word boundary value come from? Well, because we need to complement. Ultimately, we need to complement this equation with boundary conditions. And I'll illustrate 3 types of boundary conditions here in one picture. So probably it will ring bells for some of you. So this condition is the so-called free free surface, or maybe a bit more specialized, the term Neumann boundary condition. Neumann condition. So mathematicians like to refer to this as a Neumann condition, but in applications you may hear this free surface or something like that. Then there may be a part of the region which is simply attached to something. So this is often referred to as the deadlock condition or zero displacement. Okay, can you tell me what it is in terms of U? Here we have the normal derivative of U, so this is the gradient times the normal, stereo normal for the free surface. So if I have zero displacement, this speaks for itself, right? So I have U equals 0 there. Okay, and this is often referred to as the Dirichlet condition. Otherwise it will get too small. It won't be visible. So zero displacement. Zero displacement, Dirichlet condition. And then there is also another type of condition that I can make set on some part of this boundary, which turns into either one or the other. It's actually the most general type, if you like. It's the so-called Robin condition. Okay, so this is 0. Alpha is just some constant parameter, and you get this condition if alpha is 0, and you get that condition if alpha is infinity. So if I divide by alpha, and I set 1 over alpha to 0. Alpha is, I just want to make it. I mean, it's fine. Yeah, that's okay. I don't care. It's just to illustrate it. You may have no part of the boundary with this condition, or no part of the boundary with this condition. It could be Neumann everywhere, Dirichlet everywhere, or Robin everywhere. Okay, at this point, could ask you to put your hand up if everything is clear up to this point. I mean, generally, clear sort of in general terms, please. Okay. So yeah, thanks. So I'd like to encourage those who didn't talk to me in the coffee break, just so we can stay on the same page for the next section. Okay. I don't care. I just said that it's a constant number. It's constant. Huh? Yeah. I'm gonna do the non-dimensionalization. I said the non-dimensionalization is coming. I wanted to illustrate the term boundary value problem. Yeah, right. So this is a boundary value problem, and it's on a lowercase u, not capital U, because I've done something to the original problem. What? I will do that. I will do this essentially in a second. Okay. So this is to illustrate the term boundary value problem. So now, how do I get from one picture, from that picture with the bounded region, which is shaded and has size, typical size L, capital L? How do I get to this guy? Right. So very simply, I take
Open region is a free surface.
Open. Yeah, the question whether it's open or closed is not very relevant here. You can think of this as being open everywhere. These conditions are not about it being open or not. These conditions are about some quantitative behavior of the quantitative description of the behavior of the displacement when I get close to this part of the boundary. You can think of it as open, or you can think of it as closed, or it's not relevant. It's about what happens to the solution when I get to this point. So when I drew this, it doesn't mean that I just close this part of the boundary. I drew this, I should have used a different color, simply. Sorry, that might have been confusing. I don't mean to close it or that it was open and I closed it somehow. No, I'm just indicating that on some part of the boundary, it's just a different condition set. Does it make sense? Okay, so right, so I'll think of the variable that lives in this region as x tilde. And remember we had this, okay, a copy, a kind of a region that looks similarly in shape. Sorry, I can't maybe copy it exactly. But have the typical size, capital L. I'll think of the points in this region as being labeled by x. They were labeled by x from the very beginning. Remember, I said x1, x2, x3. So it's not the same label. X is a label in the original region, the physical region, and x tilde is a label in some kind of other one that I'm about to produce from this one. So how do I get from here to here, given that they have the same shape? They have the same shape, but have different sizes, right? So, in fact, the different sizes doesn't make sense here, because what I'm going to say is that this region has a size, and that region, well, it has also a size, but not measured in meters anymore, right? So what I'm going to do is I'm going to write x tilde equals x over L, and that's going to get rid of my, that's going to hide my length scale somehow, right? I'm gonna relate x, which is measured in meters, x it's measured in meters by L, which is measured in meters as well. So I'm gonna get a number, not 1, 10, 100, some number. So what happens when I do this? So you can see that here this is not a physical region anymore. It's a region. It's a kind of mathematical abstraction, if you like, mathematical region that I will use to study my problem. So, but I won't have L here. L is hidden somewhere in the formulation, and I want to see where now, right? So, so what happens to the Laplacian with respect to x? Remember, I had the Laplacian. I'm going to put x here. I didn't have it before, but I'm going to put it, right? Because I now have x and x tilde. What happens to it? I'll give you 5 seconds. Those people who think this is straightforward, please don't say anything. Okay, so remember the Laplacian was the sum of second derivatives with respect to x1, x2, x3. If I have x1 tilde, x2 tilde, x3 tilde is x1 over L, x2 over L, x3 over L. Those partial derivatives are going to just throw out some constants, right? When I differentiate. So it's going to, every differentiation is going to throw out 1 over L, and I do it twice, and then I add them together. That doesn't change the fact that I have 1 over L squared as a result. So this is 1 over L squared. The Laplacian effect with respect to x tilde now of this function lowercase u, which lives here, that I introduce by this formula. That I relate to u, capital U, via this formula. Does this make sense? So it's a simple change of variables that we're all familiar with from year one calculus. Just take coordinates, stretch them somehow. Think of this as a stretching factor. And you get new coordinates, but physically what it means, that since the stretching factor was a dimensional quantity measured in meters, after stretching we will get a non-dimensional quantity, x tilde. I could also non-dimensionalize u at this point. Some attentive listeners will note that I haven't done anything to u. So strictly speaking, yes, to completely non-dimensionalize the problem, I have to do that to lowercase u as well. I have to divide capital U by L as well. But I won't do that right now. So I'll have a because I don't want to make things complicated for you, right? In fact, it won't matter for me because my problem is linear. In a non-linear problem, it would matter. Because I would actually get some additional parameters popping up. But in a linear problem, it doesn't matter that I multiply this by any constant, so I just choose that constant to be 1. Okay, so does this make sense? Yeah. So I have about 5 minutes left. Okay. So what I'm gonna, yeah. So I have this region. Let's bounded region now. So I'm gonna have to sort of depart from those plane wave exponents. I need to introduce a more general form for my wave, for those vibrations that are observed in this bounded region. So what I'm going to do, and it's a voluntary act really. You can ask me why, how on earth you decided to do this. Well, because you realize that you can't proceed without doing something, looking at some more complicated shapes for your functions. So I'm going to replace e to the k dot x minus omega t by a more general I'm going to use this fancy word here, ansatz. Does this sound familiar to you? I don't know if there are any Germans in the audience, but ansatz means for a German it means when you put some vegetables and chop them, you have prepared them to put in a soup. That's ansatz, right? You have prepared your vegetables, right? Not just you have done something to them and they're ready to go. So this is a kind of form that was ready to go into the equation. I'm gonna use a different form here. So a different ansatz, more general ansatz. Of course, that guy is a particular case of this one, where W is e to the ik dot x, but I'm just gonna admit more general W's. So then I'm gonna use lowercase w as a scale version of capital W, right? But in complete analogy with uppercase U and lowercase u, with this. I just have to use other letters for them because the full capital U is that function multiplied by that time harmonic exponent. And then the equation looks like so. You can check it. It's a simple exercise. right? So I can drop now that exponent. I have kind of sort of managed to forget about the time for a second, but actually the time is not totally forgotten. It's encoded in this omega here. Because omega is the kind of variable that measured in the units inverse units of time. So, but I'm going to drop this exponent, of course, because I can. It doesn't vanish. So, and I can write the equation like so. So now these guys, you can imagine, is dimensionless. So all these experiments, they kind of make things pop up that without us doing much, that acquire some meaning, that make us think about what they actually mean, because surely if you have lots of dimensional quantities, then put them together and end up with a non-dimensional one, then it must mean something, right? It doesn't happen by accident. Okay, so this is dimensionless, and I'm going to label this by Z. That's where the Z comes in, right? There was a comment about the Z. Please show how Z. Okay, so here it is. Z, and I'm just going to illustrate that the units of Z are the units of rho over mu, the unit times the units of omega squared times the units of L squared, and that's, I'll give you 5 seconds. Okay, so you can think while I write. Remember, this was mu over rho was meters per second squared. Then we have inverse second squared. Then we have meters squared. So this is dimensionless. So another way of looking at this constant, and it's a useful way of looking at it, so I'll mention it, is to say that rho omega squared over mu is this guy. So maybe, so C minus 2. C is the wave speed. T is the period in time period. The equivalent of lambda, the wavelength, but for time. And this is 2 pi over ct squared. Oh, sorry, did I label the wavelength by lambda? No, that's good. So I didn't mean to. The reason is because I want to call, yes, I want to get it now. I want to introduce it now, right? So now this is where it comes, the wavelength. Okay, so this is wavelength. And this is C is the wave speed in free space. I have to add this free space because I have bound region, so I need to kind of refer to the original problem where waves are propagating in the free space. Right, so this is, remember this is square root of mu over rho. It was the wave speed in free space. So in other words, Z, oh sorry, I erased it, but Z is 4 pi squared L over lambda squared. And we have a ratio of 2 length scales, capital L and lambda. So the size of the region, the original physical region, and the wavelength. I don't really care about 4 pi squared. It's just a constant. So So, and in this problem, and I'll conclude with this. So here, L over lambda actually takes, in a bounded region, it takes a discrete set of values, ultimately. So, those are the values that give us those frequencies that I referred to when I talked about the drum. And so, since it's a discrete set of values, so just points on a real line, L over lambda going to 0 doesn't yield really anything, unless I start making my model more complicated by introducing some other features into it. So, but at the moment it doesn't yield anything interesting. And L over lambda going to infinity. So this means that the waves are short relative to the size of the region. So this will give us short wave eigenfunctions. So that it's a sequence actually that goes to infinity, and as we move along the sequence towards infinity, we will get short wave eigenfunctions. For example, in terms of space here, so for example, the so-called, I think some people in the audience might have heard about this, will have heard about this, is whispering gallery modes. Have you heard about this? So when you go into an enclosed space and get close to the boundary and shout, sort of slightly at an angle to the boundary, you can hear what I mean, if it's sufficiently large and you put something in the middle so the waves don't bounce off the other side of the medium, then you will hear what you said after a while, because the waves will travel along the boundary. Those are the so-called whispering gallery modes, and they're high frequency short wave eigenfunctions. Okay. So actually, these can be constructed explicitly, but in a kind of asymptotic way, explicitly but approximately, using the so-called Keller-Rubinau method. And I'll stop with this today. So Keller, you can look it up, and I can give you a reference if you are interested. So this is. You can actually, there is a way to construct these eigenfunctions asymptotically. Okay, and it's a known method in wave propagation, community, structure community. I may even venture to say that it's known in the tectonic seismology community. Right? So and I'll stop at this point. Just to share my own session. So if there's a quick question, I can take it. If not, we'll discuss this in the coffee break.